Hello everyone, and thank you for joining me in this video short where we're going to discuss sorting and sorting algorithms. Particularly in this PowerPoint deck, we're going to look at a number of popular sorting algorithms, and we're going to examine the strategies they employ as well as their performance. We'll look at their pseudocode and some actual code implementations as well. Some of the ones we'll review are bucket sort, bubble sort, insertion sort, merge sort, quicksort, and selection sort. Now, each of these sorting algorithms have a number of different pros and cons and various trade-offs, and so we'll investigate each of them in great detail. There are also a number of great coding examples that you can find in the modules as well. Each of these different sorting algorithms, again, can be classified in some way based on their scheme, based on their time complexity, based on various characteristics. So insertion sort and selection sort are very intuitive in what you might refer to as a simple sorting algorithm. When you look at the sorting algorithm itself, it makes sense. It's very clear and intuitive as a human being. However, generally speaking, they're not quite as efficient, at least in the worst case, as compared to some of our other sorting algorithms. Some of the more efficient sorting algorithms use a variety of different advanced algorithmic schemes, such as divide and conquer. Merge sort and quicksort both use that approach. Heap sort uses a data structure referred to as a heap, something we're going to cover later on in this class. It leverages this data structure to implement an efficient sorting algorithm. There are other intuitive, let's say, maybe simple, bubble sort sorting algorithms such as bubble sort, shell sort, and comb sort. Algorithms you might refer to as distribution sorts would be things such as bucket sort and radix sort. Here is a table identifying some of these common and popular sorting algorithms, as well as their associated time complexities for their best case, worst case, and average case scenarios. Again, here the cases are dependent on the different types of inputs they might receive. So here, example, merge sort, a sorting algorithm where we employ a divide and conquer strategy. Best case scenario is n log n, but worst case scenario is also n log n. Note that some of the other sorting algorithms, such as bubble sort, might have a worst case sorting algorithm that's quadratic, which is generally not that efficient within this context. But the best case is pretty good, right? Big O of n, linear time complexity. All right, so from each of these, we can see that different strategies are probably used because we see a variety of time complexities for these different cases, best case, average case, and worst case. Right? So I encourage you to investigate these examples within this PowerPoint deck and look at the code, look at the pseudocode, and look at the time complexity analysis. Make sure that it makes sense and that you understand it, and then dive into some of the coding examples as well, so you can see these sorting algorithms in action. All right, thank you for joining me in this video short, and I'll see you in the next episode.